Touch the leg, everybody. So now I'm going to start one new chapter, that is alternating current. Okay, so this is the result of electromechanical inductions. So just now we have done with AC generator, right? When we talk about AC generator, we say that this is an alternating voltage. This is what we call as alternating voltage, EMFs. And Vm is the maximum voltage, and sine omega t, this is amplitude of voltage, or we call it as a maximum voltage, and this is angular frequency. So this is what we talk about alternating voltage. This is what we call as alternating voltage. And I told you this is the outcome of what we call as electromagnetic inductions. We have studied direct current. So we talk about two kinds of current: direct current and alternating current. All right, direct current and alternating currents. So let me give you a brief the differences between these two. Direct current means it's a steady current. Steady means steady current, right? Unchanging current. Like say I'll be having a 2 amperes. So you'll be getting a 2 ampere continuously, right? So alternating current means the voltage change, current changes, right? So current change from 2A to 0. Then to minus 2 amperes, then 0, and then to 2A. So this is how it goes alternating. Alright, so this is a huge significance. Why you prefer alternating current means normally we don't get power from nearby towns. It is normally being generated from very far from towns. Alright, so alternating current has this, right? You can increase a voltage, you can decrease a voltage. So this is what we studied in the case of power transmission in maybe chapter 3, right? So what I can do if I use alternating currents is one of the most important significance is that you can supply or you can transmit a alternating current to a very long distance without losing much power, right? So this is the why, because I can increase the voltage and I can supply a power with the maximum voltage with the minimum current, right? So this is how we could able to minimize power loss. So this is the a very important significance of alternating current, right? Alternating voltage, right? So this is what we have. So in this chapter, what we are going to study is applying alternating voltage to pure resistor, applying alternating voltage to pure inductors and capacitors, and then also we are going to supply this to the series LCR circuit, and this is how we are going to do, right? So we would like to study the action, right? What about if I apply alternating voltage to a resistor, right? And what about power? This all we are going to study. So the first we would like to study is the alternating voltage applied to resistors, pure resistors. So this is what we have. So so this is what we have. So I have R is a resistance. R is a resistance, and this indicates alternating voltage. So I would like to write here, this sign is a sign, this sign represents a sine curve, this is alternating voltage. This is what we call as alternating voltage, and alternating power source is applied to resistors, a lot resistors. And now what I'm going to do is what I'm going to do is this V is equal to applying the Kirchhoff's rules. This V is equal to IR. This V is instantaneous voltage. And this is instantaneous currents. R is resistance, or R is resistance. This is what we have. And now we have to figure out, since this is an alternating power source, I can rewrite this into, alright, this is what we have. Alright, applying this. Alright, so therefore, this is what I have, right? I am, I'm sorry, this is, right? I is sin t. And now look at here, this Vm by R cross is equal to maximum current. This is the maximum. This is what we call amplitude of current, right? This is from Ohm's law, right? This is from Ohm's law, right? Ohm's law. This is from Ohm's law. So I is equal to Im. This is what we have. So for a pure resistor, I have this is a voltage you supply. And this is instantaneous currents. And look at here, both are sinusoidal in nature. So these both we are sinusoidal. When I talk about a sinusoidals, it vary like a sine waves, right? This means, which implies this vary like sine wave. This vary like sine waves. So look at here, this V is equal to Vm sin omega t, I is to I am sin omega t. So both are in phase. The voltage and the currents alternate or vary at the same time, right? That means they vary together, right? They vary together. I mean, they just say this implies that voltage, instantaneous voltage and instantaneous current vary at the same time, right? Vary at the same time, right? That means if a maximum current, maximum voltage, zero current, zero voltage, zero current, zero voltage, then minus I maximum minus V maximum, this is how it goes, right? So this is alternating, right? This is what we call as alternating. Now look at here, what about average voltage, right? So average voltage in a cycles, right? I just say average voltage in a cycle is going to become zero. Why? Because this is sinusoidal in nature, right? And what about average current, right? Average current in a cycle is also zero. Why? Because this is how it goes, right? Minus is going to become plus, minus is going to become zero. So this is what we have, right? And however, look at here. However, the average power is going to become zero, right? So first I will talk about instantaneous power. So from Joule's law of heating, right? Say Joule's heatings. So power is equal to I square R. Power is equal to I square R. Now this is instantaneous power. This is instantaneous power. Power at time t, right? Instantaneous power. The definition of instantaneous power is power at given time t. Alright, so therefore this is equal to Im sine omega t whole square r. Okay, and now look at here, this is equal to Im square r sine square omega t. This is power, right? This is instantaneous power. Now what about average power? Average power in a cycle, right? What about average power in a cycle, right? So average power is going to become, so this is average power, which is equal to P bar. This is average power. So average power is equal to Im R. This is average power, right? So what is the average? So I'm not going to do trigonometry, identity and prove you this. I will state right. The average of sine 2 omega t is equal to half. Average of sine 2 omega t is half. So therefore average power is equal to I square m r divided by 2, and average power is equal to I am root 2 whole square r. And then now what I'm going to do here is the average power is not going to become 0, right? So this is not equal to 0. So however, average power in a cycle is not equal to 0. What is the average power? This is going to become average power. So therefore, I am going to write one more. This is equal to IRMS squared divided by R, where IRMS is equal to divided by root 2, which is we call as a root mean square. And this is what we call as root mean square, right? This is what we call as root mean square. I will write here what is IRMS, alright? So IRMS is root mean square. This is one way of taking average. This is one way of taking average, alright? RMS. So therefore, the power is equal to, average power is equal to IRMS square, or sometimes we represent this. So I stands for IRMS. That means capital I stands for IRMS. So maximum current is equal to root 2 multiplied by RMS, and maximum voltage is also equal to root 2 VRMS. That you should keep in mind. So therefore I can rewrite the power. Again I will rewrite the power. Power can be written as, average power can be written as, average power can be written as a VI, where V is equal to VRMS, where I is equal to IRMS. So this is the power. This is the power. Alright. So this is the power, right? Average power. So there normally, therefore, let me tell you the significance of IRMS, right? So we normally say that we get a voltage of, in India we normally get voltage of 220 volt. This 220 volt is nothing but VRMS, right? This is nothing but VRMS. So this is what we have. So therefore, this is for, so VRMS becomes steady, right? This is for VRMS, and this is for IRMS. So VRMS and IRMS are the steady current. This represents steady current and voltage. Alright, so this is what we have. This is what we have, right? IRMS, VRMS, I've given you all, relation also I've given, right? So now having this is what we have. Or this is what I would like to show you now, right? And So therefore, this is the curve. This is the average voltage. So look at here. This is the voltage and the current. Current and the voltage are in phase. We call it as in phase. Why? In case of pure resistor, in case of pure resistor, current, instantaneous current, voltage and instantaneous current are in phase, and that means they go together, which implies go together. Alright, this is what we have. So therefore, this is the power, right? This is the power. So there is an average power. There is an average power, right? So we talk about average power dissipations in a cycle. So this is a very important diagram, right? Positive into positive is positive, negative into negative is positive. Alright, so in a cycle, for pure resistors, we have a power dissipation, average power dissipation. Alright, this is what we have. Alright, this is diagram tells you everything here, right? So now next very important is one new concept which we are going to do is rotating vectors or phasor, right? Rotating vector of, this is a very important concept for inductors, capacitors and a series LCR circuit. So I say a phasor is a vector. Normally current is a scalar or voltage is a phasor. Now here we try to figure out current is a vector and we try to figure out voltage is a vectors, right? This is what kind of vector? Rotating vectors, right? So a phasor is a vector which rotates about origins. This is the current phasor, this is the voltage phasor. So I just say V is the voltage phasor and I is current phasor, right? Then this is the vector which rotates about origins with angular speed omega. With angular speed omega. This is very important. With angular speed omega. So this is how it rotates. So therefore, and then one more point I would like to tell you is, since while rotating, its instantaneous value, that is for voltage and instantaneous current, keeps on changing. That means instantaneous voltage and instantaneous current doesn't remain same. This changes with rotations, and rotation is a very good example of cyclic process, right? So this is what I have, right? And the amplitude, right? The length of these vectors, right? Length of these two vectors represents the amplitudes. This is the I just say this to a phasor vector, right? Phasor, and the vertical components component represents instantaneous value, right? Instantaneous value at time t, and the length second part, length of V vector V and vector I represents amplitude or maximum voltage or current. This is very important, right? So therefore, when it rotates, at this point you will be getting a maximum value. So therefore, this is going to be a maximum. Then when you reach here, it is going to become 0. Reach here minus. This is how it goes. So I say vertical component tells you instantaneous value. So this is what we talk about. All right. This is what we have. But what I try to figure out with the sine wave, right? Look at it. Look at here. Sine wave At this point, you will be having this value, right? This is instantaneous value of voltage. This is the instantaneous value of current. Now, when you reach here, instantaneous value is going to become this is going to become this maximum amplitude, right? And the current is going to become this. And when you rotate this side, then you will become 0 again. It will become 0. And then when you reach at this point, you will be getting this is going to become an maximum. This is going to become a maximum of current. This is how it goes. So this goes together, right? So this vector is what we call as a Phasor vector, right? So due to which, because of which, therefore I say that instantaneous value, right? Instantaneous value which I told you, this is going to represent by Vm sine omega t. And I is equal to Im sine omega t, and Im and Vm represents amplitude, that is a length. So this has to be assigned functions. Why? Because vertical component tells you the magnitude, instantaneous value, right? So this is the point. So therefore I say the vertical component of a Phasor V and I represents the sinusoidally varying quantity V and I. So that is what we talk. The magnitude of a value Phasor V and I represents amplitude or the peak value. So that means the length of these two length of V and I represent the maximum or the peak value. This is the point, right? So this is what I have. So when you rotate, then the instantaneous value keep on changing, right? So it is going in a cyclic form. It is going in a cyclic, that means it goes to maximum, then 0, then in a negative, goes on like this. So this is again a nice representation, right? So now let me tell you regarding pure resistor. This is for pure resistor. This is for pure resistor. In case of pure resistors, voltage and current go together, right? So they all go together. When voltage is 0, current is 0. When voltage is maximum, current is maximum. When voltage is 0, current is 0. When voltage is in a negative direction, the current is. So this represents Phasor diagram method, right? Phasor diagram method for pure resistor. For pure resistor. So that's the. I'll show you this. I'll show you here. I'll represent this is, let's say, a voltage Phasor, and this represents current Phasors. At any time t, phase is going to become omega t. I say at any time t, phase is omega t. So now, what is the value of V at time t? Value of a V at time t is going to become this value, right? So this is going to become V m sine omega t. All right. What is the value of I at time t? I m sine omega t. Now what is Vm? Vm is represent the length of V, and Im represents length of I. So this is the point. So they go together. Rotating, right? So this is a cyclic. This is what we call a cyclic. Now next I would like to do is for pure inductors. For pure inductor, all right. For pure inductor. So this is for pure inductor, and this is alternating voltage you are supplying, and in inductor having inductance L. This is an inductor having inductance L. Inductor of inductance L, and we say that this inductor has almost zero current, zero resistance, so it is pure inductance. All right. So I say inductor has almost zero resistance, almost zero resistance, therefore what? Therefore it is pure inductors. Alright, this is what we call as pure inductors. And this is input voltage. This is the voltage you are going to supply. This is the voltage you are going to supply. And again, I'm using a Kirchhoff's rule. So that is, so what is that? Is 0, that is equal to V minus L di by dt is equal to 0, and V is equal to L di by dt. Okay, now what is V? And I'll just say L di by dt is equal to Vm sine omega t, and di is equal to Vm divided by L sine omega t dt. So this is the instantaneous change of voltage in a small interval of time dt. This is the instantaneous change. This is instantaneous change of current in a small interval, instantaneous interval of time at instantaneous time, at instantaneous. So I can just say this is the instantaneous change of currents due to at instantaneous time. All right. So now I would like to integrate this. I would like to integrate this. When I integrate this, and then this would be equal to Vml, and omega comes down, minus cos omega t, and omega goes down plus some constants. So whenever it is indefinite integrals, we have to put constants. However, this constant becomes 0 now. Why? Because it is alternating, right? It is alternating, so constant is become 0. So finally, I would like to write. So finally, what we can write is I is equal to Vm omega minus cos omega t. Alright, so therefore this is equal to Vm, we call it as XL, this is what we call as sine omega t minus pi by 2. So I write here XL is what we call as inductive reactance. Inductive reactance, which is equal to 1 by L omega. 1 by L omega. And minus cos omega t is written as, this is the identity, right? I'm not going to explain much. You need to know this. Alright. So this is what I have now. So having this, I can say that this is equal to, I is equal to Im sine omega t minus pi by 2. So unlike pure resistor, now in case of inductor, what we get is, this is the voltage you are going to give you, voltage that you are going to supply, and a current in a circuit would becomes that means this implies that current is behind. This implies that the current is behind. This implies that current is behind voltage by pi by 2. Alright, this implies that current is behind voltage by pi by 2. And this is also very important, right? Inductive reactance is given by the inductance and angular frequencies. Alright, so the inductive reactance is also affected by angular frequency, right? So this is one very important, and this is what we have, right? So unlike pure resistors, both the voltage and currents doesn't go together. If one is maximum, another is zero. Right? So this is one. So why? Because the voltage is ahead of current. Current is behind voltage. So this is what we have. This is what we have. We try to represent in terms of a Phasor diagram method. Right? We try to represent in terms of Phasor diagram methods. So this is the voltage, and this is the current. So current is behind voltage. So current is behind voltage by 90 degree. And this is the instantaneous value of voltage. Current. This is the instantaneous value of voltage. I say this is the instantaneous value of voltage. This is the instantaneous value of currents, and then current at the instant of time t1, voltage is at this point, current is at that point, so the difference is of pi by 2. And this is the Phasor diagram method. This is the sine curve. This is the sine curve, right? So you would say that since this is phase difference is 90 degree, if one is maximum, another one is zero. So that's simple, right? If I turn this right here, if the voltage is this, if this is voltage and this is current, this is phase difference is 90 degrees. So this is what we have in case of. Alright, now let's talk about, this is the Phasor diagram method, right? Representation. All the time. Now what about average power, right? What about average power, right? I say average voltage is going to become zero. Average voltage in a cycle is zero. Average current in a cycle is zero. What about average power, right? So now so instantaneous power is VI. Instantaneous power current is VI. So V is equal to Vm sine omega t. I is Im minus cos omega t, and that's power is minus Vm Im sine omega t cos omega t, and then this is equal to Vm Im divided by 2 sine 2 omega t. This is the instantaneous power. The average power is given by minus Vm Im divided by 2 average of 2 sine. What is the average of 2 sine omega t? Average of any sine function is 0. Average of any sine or cos function is 0. So therefore 0, which implies average of sine 2 omega t is equal to 0, right? So this is, so therefore average power is become 0. Average power is become 0, and we say that since average power is 0, since average power is 0, so we will say that current involved is what we call as a wattless current. So the current involved is what we call as a wattless current. So inductor has a wattless current. Why? Because even there is a current is there, but then average power dissipation become 0. So this is again one way of showing you this, right? This is a colorful diagram, right? Now this is what I have. So I would like to show you, this is there in your textbook, and I would like to show you how the power becomes 0. How power in a cycle becomes 0, right? So this is a one case. Current goes on changing, right? So in this case, the energy is being taken out from a source to from a source energy is given to a solenoid in a one cycle, and the next quarter cycle, this is one quarter cycle, next quarter cycle's energy is given back to source. Alright, and the next third quarter cycle, this is first quarter, second quarter, third quarter cycle, again energy is given back to a source in opposite directions, magnetic field direction. So you see that north pole and south pole has interchanged. Alright, and in a For quarter periods, energy is returned back to the source. Alright, so overall energy would be 0, right? So this is diagram which we would like to tell you, right? So voltage is positive, current is positive, power, that means power absorbed from source, and voltage is current is positive, voltage is negative, and then power is negative. That means power returned back to the source. Here voltage is negative, current is also negative, power is positive. Again power feedback to the source, feedback to solenoid from source, and current is voltage is positive, current is negative, and then power is negative. That means power returned back to the source. So overall, plus minus overall, power becomes 0, right? This is again one more diagram, right? This is again one more diagram. This is what we had. Same diagram, right? So with this, I come to an end of pure inductors. So next class we would like to do for pure capacitors and then LCR circuit. Thank you.